is a deductive argument in our previous lesson, where we start with two premises, premise 1, premise 2, and conclusion. Now, the validity of this particular argument containing 3 sentences does not depend on the truth and falsity. It means that we don't look at whether it is true or false. Because if the premises are true, the conclusion cannot be false if this particular argument is valid. So usually, to determine the validity, in examples like this, it is necessary to separate the statements into parts in much the same way that you separate declarative sentences into subjects and predicates. So these are what we're going to highlight or focus on today, subjects and predicates. As far as you can remember, when we try to identify whether this argument is valid or not, we separate our subject and our predicate. Here, actually, all men here is our subject. So this is our A, and this is what describes our subject, that is our B. So it should follow this form. Yes? Then we are going to have an example of this group. All men are mortal. So Socrates is a man. Socrates is not mentioned in the first sentence. So this is C. And man is mentioned in the first sentence. Is part of all men. So this is going to be A. And Socrates is C. Again, because it is C here in the second sentence, and mortal is B in the first sentence. So this is a valid argument because it follows the form A, B, C, A, C, B. What does this mean? It means that if the premises are true, the conclusion cannot be false. For example, here, this one is true. All men are mortal. Mortal means we have limited energy and limited time. Socrates is a man is also true. Okay, then Socrates is mortal is also true. So if the premises are true, the conclusion cannot be false. That's the meaning of valid argument. Okay, so you must also analyze and understand the special role played by words that denote quantities, such as all or some. In this scenario here, in this argument, the quantifier that we use is all. So we will be looking at this in our subsequent discussions, how we are going to use all and some or there exists. So the symbolic analysis of predicates and quantified statements. When I say quantified statements, these statements use quantifiers like all and some. I'm going to have several examples of this in our next discussion. So the symbolic analysis of predicates and quantified statements is called the predicate calculus or predicate logic. So what are these predicates and what are quantified statements? So let's look at some of the examples of this. Okay, so let's start with this sentence. He is a college student. This particular sentence is just a sentence. We cannot call this as a statement. Unless otherwise, we're going to define this he here. Right? So he, we don't know who is he. Could be he, she, or it, they, we. So all pronouns, if these pronouns are not defined, the sentence cannot be called a statement because we cannot assign true or false. Similarly, x plus y is greater than 0. is also not a statement, but it is a sentence. It is an inequality. Okay? It's not a sentence because the truth value depends on the values of the variables x and y, which we don't know in this particular example. If I'm going to assign x is equal to 4 and y is equal to 5, then it becomes a statement. And it's going to be true because 4 plus 5 is equal to 9, which is greater than 0. Okay, so in grammar, the word predicate is that part of the sentence that describes the subject. It gives information about the subject. Okay, so subject is the focus of the sentence. This is what we're talking about. Here, for example, James is a student at Bedford College. James is our subject. And the phrase is a student at Bedford College is the predicate. So is a student at Bedford College describes our subject James. So it gives information about our subject. Okay, so that is the meaning of predicate in English. Or it is a part of a sentence from which the subject is removed. So if you're going to remove James, the remaining part of the sentence is the predicate. But in logic, specifically, predicates can be obtained by removing some or all of the nouns from a statement. So in logic, it's a bit different. In grammar, in English, purely a predicate is part of the sentence. It means all the words without the subject, removing the subject. For example, he is an engineer. Our subject is he. Okay? If you're going to remove he, the remaining is our predicate. So these words describe our subject he. So is an engineer is our predicate in this sentence. I hope that is clear. So we can remove some. In here we have James and Bedford College. So we can remove Bedford College or James when we are dealing with predicates in logic. So it's a little bit different. We can remove the subject or we can remove all other nouns as well. Okay? So let's have some examples here. Now, our original sentence is James is a student at Bedford College. Or we can also say Muhammad is a student at Majan University College. Okay, so here in the first sentence, we remove only the subject. James is removed. Okay, in the second sentence, we remove James and we remove as well Bedford College. It becomes Y. So that is the meaning of this statement here. That in logic, predicates can be obtained by removing some or all of the nouns from a statement. But the predicates that we're talking about here actually now has a corresponding variable. Okay, so usually when we express our sentence in predicate form, we have a variable and we have the predicate. Okay, we combine together. But our nouns or our subjects like James, Bedford College will become variables. So that is the difference in logic. We are changing actually our subject and other nouns into variables. So we are not just dealing with a predicate or predicates. We are dealing with a whole sentence actually, where the subject or some other nouns are changed into variables, like here, okay? So how do we answer this? How do we change this? How do we translate these sentences with variables into predicate form? First is to have our predicate symbol. Okay, this is our predicate. As I mentioned, predicate is a part of a sentence that describes our subject. Here, our subject is X because we deleted James and changed into X. Okay, so our predicate, we can use P or any letter actually, is a student at Bedford College. That is our P. Okay, so our answer here would be like this. We are translating this sentence into predicate form. So we start from the right. This is the subject inside the open and close parentheses. And we go to the left. Okay, and the left is our predicate. So our predicate is a student at Bedford College. So P will be here outside. Okay, so you are going to read from right to left. It's how you write in Arabic. So X, that's the subject, has the property of P. So what is P? Is a student at Bedford College. So it has the property of P. What is it? What is the property here? Is a student at Bedford College. So basically the formula is like this. Subject is inside and we go to the predicate outside. Okay, so inside is the subject. In this case, our subject is X. Then we go to the left, we write our predicate. Here, as you can see, we have two variables. James is a student at Bedford College. James is deleted, changed to X. Bedford College is changed to Y. Okay, so again, we're going to start with the subject inside. Okay, and we go to the outside left is a student at. So this one, we have to define this as well. We can make this as Q or P. Okay, so assuming that is Q, so X is a student at, this is our Q here, comma, this variable Y. Okay, so subject is X, X is a student at Q, where Y. Okay, so these are the first two predicate forms here. First one is X has the property of P. P is a student at Bedford College. That's our sentence. Second one, our Bedford College is deleted, changed to Y. So we have now two variables, X and Y. So we start with the subject, then we go to the left. X is a student at is Q, and comma, the second variable, Y. Okay, so what's the meaning of these variables here? Okay, let me write again the answer. Here the answer is X has the property of P. Here the answer is X, Q outside, then Y. Okay, so here when we have P of X or X has the property of P, X is the subject, this is the variable, and P is the predicate symbol. This one we assign this as P, and here we assign this as Q. Okay, so here we have two variables, X and Y, and Q is our predicate symbol, is a student at. So in most cases, the predicate form contains two things, variable or variables, and the predicate symbol. Okay, so please remember that. So X and Y are predicate variables that take values in appropriate sets. So X here now could be any student at Bedford College. It could be James, it could be Ahmed. So that's the difference. Okay, so in our original sentence, James is our subject. So James is a student at Bedford College. Only James we are talking about. Very specific. And here we talk about Bedford College only. Very specific. Here, X now can be any student. So that is the essence in predicate logic or predicate form. Our nouns can be any noun related to the predicate, whatever is being used as a property. Okay, here we change our subject James to X, and we change our college Bedford College to Y. So X here can be any student, and Y now can be any college. It could be Majan University College or any college in the world. So that's the difference when we have the predicate form. So when we change our variables into specific values or concrete values, when we substitute in place of these variables, then we will have a statement. Okay, for example, here, if I'm going to change this X to James, it becomes a statement. Or Muhammad, for example, it becomes a statement. Here, the same, change X to any student and change Y to any college is going to be a statement. Okay, so that's it. When we have predicate forms, our nouns become variables that can take any values. Okay, so here, for example, this is our sentence. N is a fish. How do we change this into predicate form or in predicate logic? Our sentence is N is a fish. So we let F is our predicate, is a fish. Okay, mentioned here. It could be any letter, but it's easier to use the first letter. Okay, it's easier to use the first letter. So is a fish actually describes our subject N. N is our subject, which we don't know. It could be any fish. Okay, so N there is our variable, predicate variable. So as I said, we start with the subject inside, like here, subject. So here our subject, when we have N, is a fish. This is our subject, which is a variable. So we start from there, then we go out. So predicate is on the left, that is F. It is a fish. Okay, so this is our variable, and this is our symbol, predicate symbol. Right? So I hope this is clear. So here we have N is a fish. We start from the subject, then we go to the left. Here, we already have the predicate symbol. G is greater than. This is our predicate symbol. And this is our sentence. Our sentence is M is greater than K. So we have two variables, M and K. Same here. X is a student at Y. So we'll start with the subject, M. Then we go out, our predicate. This is our predicate symbol is greater than G, comma, K. So that is our answer. M, our subject, we go to the left, our predicate, that is greater than, is G, and then the second variable is K. So comma, K. So that's the answer. Okay, so it's very simple. So for simplicity, we define a predicate to be a predicate symbol together with suitable predicate variables. This is what I'm saying. In logic, when we have the predicate form, when we write our predicate form, usually we have two things: predicate variable and the predicate symbol. Okay, so here we have the variable n, f is the symbol. So this is the predicate symbol. Is a fish, and n is the variable. This is the predicate variable. Okay, so it consists of two things generally, the variable and the symbol. So we also call this predicate form as propositional functions. So actually, these predicate forms are functions because we have the variables. And when we change our variables, it gives us some values. Okay, and also it's called as open sentences. Open because we have variables. It's open to all possible values. Like here, f of n is a function. Open sentence because n can be any value, any fish. Could be milkfish, catfish, or any fish. That's why it's open. Okay? So a predicate is a sentence that contains a finite number of variables. This is in logic, because in grammar, in English, it's a little bit different, although the concept is the same. Okay? Here, when we talk about predicate, we are talking about the whole sentence. This is not just predicate, a predicate form actually. Okay? It's a sentence that contains finite number of variables. It means you can count. Okay, and becomes a statement when specific values are substituted for the variables, like here. Here, if I'm going to change n into a specific fish, it's going to be a statement. Okay, a milkfish is a fish. So here I change n to a specific value. So it becomes a statement which is true. Okay? So that's the meaning of this. It becomes a statement when you change the variable or variables. Now the domain is the list of all possible values. Okay, set of all possible values that can be used or can be substituted in place of the variable or variables. Okay, so here n here is our subject, is our variable. So our domain here actually is the list of all fishes in the world. So in some cases, you cannot write all the domain like this. N is a fish. You cannot write all the domain because we have so many fishes in the world. Okay, so it is infinite, but the number of variables is finite. Here we have only one variable n. Here we have two variables m and k. Okay, so now let's look at this example. We're going to find the truth values of this predicate. Our predicate is x has the property of p, and that is x squared is greater than x. When I say predicate here, we're talking about the predicate form. We're talking about the whole sentence with variables. So our sentence is x squared is greater than x. Okay, it's expressed in mathematical symbols, inequality. You can, of course, change this into English sentence by saying the square of x is greater than itself. Okay, so that is our predicate form. X has the property of p, so it is x squared is greater than x. So as I said, you can write it like this: the square of x is greater than x itself. Okay, so here is greater than itself actually is our predicate. Okay, and this is our subject, the square of x. Well, we are not translating it. Our purpose here is to identify whether we have true or false using the given values. So this is our open sentence, as I said, or we call this as our predicate form. Okay, because x can be any value. If it's not mentioned, it means real numbers, all real numbers. From 0 to positive infinity, 0 to negative infinity. That's the meaning of that. When it's not mentioned, all numbers allowed. Okay, and it's here. Okay, domain set R. So the values are given. As I said, if we change our variable into a value, it's going to be a statement. So it's either true or false. So assuming we're going to change our x to 2. So this will become 2 squared greater than 2, which is 4 greater than 2, which is true. Okay. Second one is 1/2 our x. So we're changing our x to 1/2. 1/2 squared is greater than 1/2. This is 1/4 is greater than 1/2. 1/2 squared is 1/2. Multiplied by itself is 1/4. This is going to be false because 1/4 is 0.25 and 1/2 is 0.5. So it is false. The last one is our x is negative 1/2. Negative 1/2 squared is greater than negative 1/2. This is 1/4 is greater than negative 1/2, which is true. True because the one on the left is positive, is always greater than any negative value. So there are only two values which made our statement true. Okay. So it becomes a statement because we're changing it into specific values, 2, 1/2, and negative 1/2. So our truth set here of the given values are, we have 2, because here we have true, where x is equal to 2, and the other one is negative 1/2. Because when we replace x by negative 1/2, it becomes true. So that's the meaning of this truth set. So truth set means a set that contains all the values that make our predicate form true. Okay? So there are two values based on the given. Of course, if we're going to use more values, it might be true or false because these are all real numbers. The list will continue until forever. Here, we are just focusing on these values, 2, 1/2, and negative 1/2. We are not including all other numbers in this set, real numbers. Okay, so that's the meaning of truth set here. Now, quantifiers. Quantifiers like sum and all denote quantities. And these quantifiers tell for how many elements a given predicate is true. So if it is all, it means all elements. When we say all animals, it means we include all animals in the world or in the universe. When we say some animals, it means not all. It can be one, it can be two or more, but not all. Okay? So these quantifiers were first introduced by Charles Sanders Peirce and alone by Gottlob Frege. So these people, they are the ones who introduced this so-called quantifiers. Okay? So let's delve into the first quantifier. The first quantifier is using this symbol. It means universal quantifier. So all elements are included. So the keywords are all, every, each, any, or anything. It means that all elements will be included. It means that it can only be true if and only if this predicate form is true for every x in D. So this is our general form. So we will have an example or more examples for you to understand this form. So this is the form of universal quantifier. Our domain is D and our predicate is Q of X. X has the property of Q. Already I have many examples of this in the beginning. When we use James is a student at Bedford College, we change James to X and is a student at Bedford College to P. So it could be P, it could be Q. Q here is any predicate symbol. Okay? So Q could be P, Q, R, or any predicate symbol. X also can be any variable. So you can use any variable here, X, M, Y, Z, any variable. D is any variable, any domain. Okay, and X here, it means any possible value of domain. And D is the list of all possible values of X. List of all possible values of this variable. So let me just specify it here. D is list of all possible values of X here. And X is any number. For example, die. In a die, we have 1, 2, 3, 4, 5, 6. So our domain contains all of this 1, 2, 3, 4, 5, 6. And X could be any value, 2, 1, 4, 5, and so on. So 1, 2, 3, 4, 5, 6. That's the meaning of that. So domain is the list of all the possible values being talked about in the problem. X is any value in that domain. Okay, same here. But X here is not always X, as I said. It can be any variable. It can be N. So you can write it like this. For all N in the domain, here we have Q of N. Okay, so the X there can be any variable that you like to use. But usually we use X. So use X as well to avoid confusion. Okay, but remember that X there can be any variable. Okay, let's start with the first English sentence. This is our English sentence. Now we are going to use the form, this form, to change this in predicate form. Okay, this is our form, universal quantifier. Okay, for all X in D, X has the property of Q. So our sentence, all human beings are mortal. Okay, now all is the quantifier, human beings, the subject. Okay, basically the subject is this, all human beings. Okay, including the quantifier all. So this is the universal quantifier. It tells us that all human beings, we don't exclude any here. So I'm going to write the answer here. First, let H equal set of all human beings. This is the first step. You have to define your domain. Okay, define your domain. So the final answer for all X in the domain, our domain is H. Okay, comma, X has the property of Q. Okay, this is our predicate, are mortal. Okay, this one. So you can, define it or no need. Directly you write X is mortal. So is mortal is our Q. Okay, guys, please take note that we are not using the plural R. We use singular here. X is mortal. Okay, X is mortal. Because we are assuming that X here is one value. So basically, instead of all, in our predicate form, we use every. Every human being is mortal. Okay? So please remember that. Don't use R. Of course, you cannot say X are mortal because X is one value. So for all X in H, it means every human being is mortal. So we are converting to singular form. Of course, you can also define Q. Here, if you're going to define are mortal or is mortal as Q, then this will become Q of X here. You can also do that, okay? But you will have to define again. So if I'm going to do that, for example, here, this is our sentence, then we say let H equals set of all human beings. And I'm going to define Q as is mortal. Okay, this is the R mortal here. This is singular. Then this will become what? Our answer will be for all X in H. Then we have here X has the property of Q. Okay, using this original form. This is the original form as given here. For all X in D, comma, Q of X. Okay, so you can also do this, but there's no need. You define the domain, and here you just start from X. X is Q. Okay, like this one. All fishes can swim. Okay, so that is our sentence. So we let F equals set of all fishes. Or usually we can use the word fish. Fish is also singular, you know, or you can also use fishes, singular or plural. Okay, fish actually can be taken as singular or plural. All right, now here we have all. So for all X in D, we have QX. This is the original form. So our answer for all X in our domain is F. Okay, X can swim. That's the answer. Okay. So for all X in F, X can swim. That's how to do it. So we just immediately take X, and then our Q is this, can swim. This is our Q. All right, so let's have the next. Here, for all real numbers, so real numbers are, this is for all. For all real numbers, X and Y, X plus Y equals Y plus X. How do we change this into predicate form? For all real numbers, X and Y, X plus Y equals Y plus X. It means that we are talking about two real numbers. The first real number is X, the second real number is Y. For example, X is 5, Y is 2. It's correct actually when we have 5 plus 2 is equal to 2 plus 5, because this is 7, this is 7. So this talks about commutative law, actually, of addition. When we change the order, it does not change the answer. Okay, so how do we change this into predicate form? For all real numbers, X and Y, comma, X plus Y equals Y plus X. So I'll put the answer here. So there are two variables. So we have like this. For all, we have the X, and then the domain is R, real numbers. That's what we're talking about. Domain is set of all possible values of the variables X and Y. We have another variable Y. So open, for all y in the same domain. So that's how to put these two variables x and y. For all x, for all real numbers x and y, then x plus y, this one will be one group. So x plus y equals y plus x. It is the property that we're talking about, one group. Then we have to close this open parentheses towards the end. So that is our answer. It means for all real numbers, x and y, it's like and, is separated by the open parentheses, x and y, both real numbers, x plus y equals y plus x. Okay, so that's our answer. We have 2 times here our universal quantifier because we have 2 variables. And this is the property, the commutative law in one group, x plus y equals y plus x. Okay, so let's now proceed to the truth and falsity of universal statements. As I mentioned, when we have like this, it is only true if x, all the values of x satisfy. Okay, satisfy our predicate form or our statement. Okay, so here, this is our predicate form, which is now a statement. If we don't have this domain, it is just a sentence. But since the domain is given, domain is a set containing 1, 2, and 3. This whole predicate form is a statement. Okay, so if the domain is given, as mentioned before, yeah, it's very specific, then the whole sentence will be a statement. So we have to show that this statement is true using these values. As I said, all the elements of the domain should satisfy the statement to be true because all, this is universal. If there is one that does not satisfy, then the statement will be wrong. So let's use one. First element. So we have x squared greater than equal to x, that is our predicate, all right? Our q of x. So we change our x to 1. 1 squared is greater than equal to 1, which is true. Because 1 squared is 1, and 1 is greater than or equal to 1, right? So that is true. The next one is x equals 2. So this is the given predicate here. So 2 squared greater than equal to 2. 4 is greater than equal to 2, which is true. Because when we have a line below, it means or. So this means 4 is greater than 2 or 4 is equal to 2. It's either. Next is the last, x equals 3. So we have 3 squared greater than equal to 3. 9 is greater than equal to 3. It's also true. So the statement is indeed true. Okay. So the statement is true. We can conclude. So using d equals 1, 2, 3 for all x in d, x squared is greater than equal to x is true. Because we have proven when we substituted the values that all are true. Now, counterexample is any value that will make the statement wrong. And this is actually used in universal statements. That means we're going to find one example to show that this statement is wrong. Okay. All right. So let's try to find some values. Here our domain is now R, all real numbers, negative infinity to positive infinity. Here our domain is very specific. It contains 1, 2, 3 only. Here we cannot write all. It's infinite. All numbers on the line are allowed. Negative infinity, positive infinity, and 0. Okay, so let's find one value that will make this predicate form wrong. Okay, so let's say, for example, 0 or 1. Okay, any value, you can use trial and error. 1 squared is greater than equal to 1. 1 is greater than equal to 1, it is true. So the whole number 1 will not make the statement false. So let's try a number which is not a whole number. 1/2, for example, fraction. So 1/2 squared is greater than or equal to 1/2. 1/4 is greater than or equal to 1/2, which is false. Because 1/4 is 0.25, 1/2 is 0.5, it is less than 1/2. Okay, so we found a counterexample. So it is false. So this statement is wrong. For all x in real numbers in R, comma, x squared is greater than equal to x, because we have a one example here that proves that it is false indeed. You can have more examples. Okay, I think all the proper fractions will prove that this statement is wrong. So that's the meaning of that. Okay, when we find a counterexample. A counterexample is a value that will make our universal statement wrong or false. Okay, so let's now proceed to the existential quantifier. Existential quantifier use this symbol, and the most common words are some, somebody, someone, there exists, or there is a. Okay, so it means one or more, but not all. So usually we use such that, but also we can remove this if we have action words by using whose or some other words. Okay, so let me give you examples for you to understand. It's related to universal. Universal is like this. We put comma instead of such that. So instead of such that, we use comma. Here, in existential, usually we use such that. Okay, so let me show you what's the difference between these two using examples. Okay, here, as I said, we can use this common words. There is at least one, there is a, there exists. We can find a for at least one, not all, some, somebody, someone. Okay, so we can use these words. In addition to that, you can use these words as well to denote that we are talking about A quantifier, which means there exists. It means one or more, but not all. Okay. For example, we say there is a student in Math 140. So let me answer it here. There is a student in Math 140. Our keywords there are there is a. Okay, it means not all students belong to this. Not all students are taking Math 140, of course. Okay, or we can say there is a person S, settable student, such that S is a student in Math 140. Okay, so we let S equal set of all students. Okay, so we can say our answer here, S as the first letter of the students. So we use this, okay, in our domain S. This is our domain, such that X is a student in Math 140. Okay, so our predicate is this. This is our predicate, is a student in Math 140. So we can make this as our Q if you want to. Okay, like here, Q of X. Okay, or you can start from X and write Q directly. Here our Q is a student in Math 140. Okay. Now, in other examples, instead of X, as I said, you can use any variable, okay, instead of X. So in some books, actually, the answer of this will be like this. So please remember this. Here we use X. Okay, we can use other variables actually. So you can write like this, small letter S in S, such that, or no need comma, such that small s is a student in Math 140. You can also write like this. There are many sources actually where instead of X, it uses a small letter of the domain. It's the domain, capital letter, big letter, and here instead of X, we use small letter of this, which means that S here, small letter, is any value belonging to the list of all possible values. So small s here means any student. And capital letter S here, big letter S, means all students studying Math 140. Okay? So I hope that's clear. Now, what is the difference of this? When we say there is a student in Math 140, and here there exists a student in Math 140 who sings and writes. These are actually similar, but here we will not be using such that. Here, the answer, let me write again for you not to be confused. In S, such that this variable X is a student in Math 140. Or as I said, you can write like this, small letter S, capital letter S. Then continue the same. Change X to S. Okay? It's up to you. What's the difference? Here, there exists a student in Math 140. Here, we just describe. We just say there is a student. There exists a student in Math 140. But we are not telling any action, what they're doing. Yeah, we just say that there are students. Okay, or there exist students. It could be one or more, we don't know. But did we mention whether they sing, they dance, they write, they solve? No. So we use such that because all are nouns. There's a student in Math 140. Math 140 is a name of a subject, student, all nouns. Here, there is a student in Math 140, and we have verbs, some action words. Okay? So it will be different now. We will not be using this such that here. So here, there exists is this. Okay? Then open. We had this in our revision file. Here we have student in Math 140 is our X. We define our X, all students in Math 140. So X is a student in Math 140, and that student, or these students sing, so X sings, and X writes. But we use the base form of the verbs. Instead of sings, we write sing, writes, we write write. Then we close this towards the end, and we close this here. So that's the answer. So that's the difference. Because here, we are not mentioning what they're doing. We just say there is a student in Math 140. So there exists X in S such that X is a student in Math 140. But here we have who sings and writes. So we need to connect sings and writes as the predicate involving action words. Okay? So that's the difference between this. Okay, let's look at this one here. This is what I give in the revision. Some animals fly and talk. This is what I'm talking about. Some students in Math 140 sing and write. Here we have singular. There exists a student in Math 140 who sings and writes. Here we use the word some, which is plural. So we use sing and write. Okay, but this actually is the same here. There exists a student in Math 140 who sings and writes. It's just about plural and singular form. So the answer here will be the same. Student in Math 140 is our X, and sing, open and close X, and write, open and close X, then close this and close this towards the end. So that's the answer. So this is related here. Some animals fly and talk. So exactly similar here. We have verbs here. So we are not just saying that there exists an animal. We are talking about what they do here. So some, so this is the symbol. Then we define it. Our X is animal. X is an animal. And that animal, what? What does it do? Fly and talk. So fly, open and close X, and talk, open and close X, close, close. Okay, so that's the answer. So I hope you are now able to understand what is the difference when we say there is a student in Math 140. Okay, we just use this. If we have some action words like this, so we have to use this format. This one is related to what I gave a while ago in universal quantifier, but here we use there exists. Here we also have two variables, m and n. So there exist integers m and n. There are some integers m and n, as plural, such that m plus n equals m times n. This is our property here. Maybe. So we are not justifying whether it really exists. We are just going to convert to more formal form. When I say formal, you're going to change to predicate form. So to change in predicate form, we are going to remove the words there. So we're going to use this. Actually, in since we have m plus n, let's change also our variable. Okay, because usually we use x. Here we use m now and n, so there exists m in integers z. Okay, there are two variables m and n, so repeat, but change m to n, same domain. Our domain integers. Our domain here is integers. Integers symbol is z. Okay, then open and close for our property there. And then we close this towards the end. Okay, so that's how to translate this into predicate form. This is the symbolic form, or the predicate form. When I say symbolic logic, talking about the predicate logic or the predicate form. So we repeated this symbol that exists because of these two variables m and n. And we use open parentheses here, z for the integers. And for this property, we have to put in one group to identify that this is a property to be proven. Okay, m plus n equals m times n. All right, so let's proceed now to the truth and falsity of existential statements. Here, this one is a statement. Why? Because z, we know what are z. Yes? -3, -2, -1, 0, 1, 2, 3, and all negative numbers. So we talk about the domain is given. There exists n, okay, which is an integer such that the square is equal to itself. Show that this is true. So this is our statement. Instead of x, we use n. As I said, we can use any letters there. Okay, so what is the meaning of this? One or more, at least one. That's the meaning of this symbol. So to prove that this statement is true, we need to get only one. Integers are this: 0, -1, -2, -3, and so on until infinity, and positive until infinity. So you can try 1 or 0. Yes, 0 squared equals 0, 0 equals 0, it is true. You can also try 1. X is equal to 1, or n is equal to 1, because we use n here. See here, I tried 0. So here, n equals 0. N equals 1. Integers, here we have 1. So 1 squared equals 1, 1 equals 1, which is also true. So in fact, we have 2 here. So the statement is true. Right? Because in existential, we have to get at least 1 only. So even you can use only this 0 is enough to prove that it is true. I'm just giving one more example. Okay, now the second one, you're going to show that the statement is wrong. For existential statements, to show that it is wrong, we have to test all. So please remember that. We have to test all. So this is our statement. because P is given. P, very specific, from 5 to 10, nothing else. There exists M in P such that M squared equals M. Let's try 5. Okay. From P, so M squared equals M, 5 squared equals 5, false. M equals 6, second one. M squared equals M, 6 squared equals 6, which is false. Because 36 is not equal to 6, 25 is not equal to 5. Next, M equals 7, M squared equals M, 7 squared equals 7, which is false again. 49 is not equal to 7. M equals 8, 8 squared equals 8, which is false again. 64 is not equal to 8. 9 squared equals 9, again false. 81 is not equal to 9. The last one, we have 10 squared equals 10, false again. Okay? Because 100 is not equal to 10. So we have proven that this statement is false because all are false. Okay, so I hope this is clear. To prove that an existential statement is wrong or false, you have to show all. To show that it is true, we have to get at least one, like what I did here. Okay, so now let's proceed to formal versus informal. As mentioned before, formal is the predicate form. Informal is the English sentence. So this one is formal. These are the predicate forms. This is B here, this is C. Okay. This one is B. And here we have C. All right, so it's very easy to change from formal to informal. Just left to right. So start from here, you say all, then the domain are real numbers, have squares greater than or equal to 0. To 0. Yes, from left to right only. This is the informal. So we are changing our predicate form to English sentence or informal. That's for letter A. Left to right. Real numbers because of R. Half squares because x squared. If it was x cubed, you're going to say half cubes. If it was fourth or fifth, we're going to say powers of. Okay? Powers of 10 if it was x to the 10th. Here again from left to right. So all real numbers because we have R have squares not equal to -1. Here you can use some or you can use there exists. Okay, you can say there exists because of this symbol or some. an integer because singular. If you're going to use some, you're going to say some integers whose square is equal to itself. Why square equal to itself? Because m squared is equal to m. So we square m. We talk about the m here as any integer. So there exists an integer whose square is equal to itself. Or you can also say some integers have squares equal to itself. You can also do that. Okay, it's up to you. So this is what I'm saying, that you can have your own way of changing from predicate form to English sentence. You can use different words as long as it means the same, it is correct. See here, you can use every also. Instead of saying greater than equal to 0, you can use the word non-negative, because greater than equal to 0 is non-negative. So you can use every, any, or each. Same here. Instead of saying not equal to, you can start with no. No real numbers have squares equal to -1 because of this, not equal to. Okay, so you can use no in the beginning. It's equivalent to all or not. Okay. This is what I'm saying. You can use some instead of there exists. You can say some, then use the plural. You cannot say some integer. Some integers. Also, sometimes we use some integer, but it doesn't sound good. We usually use the plural after some. Some integers, okay, equal their own squares or have squares equal to themselves. Okay. An example of that is 0 or 1. Now let's have the opposite. The opposite are here. All triangles have 3 sides. Okay. So this is the quantifier. So all in T. So that means triangles here, all triangles is T. X has 3 sides. You can even do this one, 3 sides, okay? Or you can also use small letter t like this. As I mentioned a while ago, it's also correct. Instead of using X, we use small letter t, and we use also small letter t here. It's correct. But to be consistent, use X, so you will not be confused. Now, no dogs have wings. So here, let T equals set of all triangles. Please don't forget this in your test. When you are answering, you have to define the variables. Let let, the domain, it's the domain. So we know what is the meaning of T that you use there. Here, the first step is to change this to all. All dogs do not have wings. Okay, so let the set of all dogs. Always define the domain. So the answer will be for all x in D. So in D, x does not have wings. Okay. So that's the answer. I gave many examples of this before. The last one there, some programs are structured. So let P set of all equals set of all programs. So some is the keyword. Answer will be like this in P. So some programs. Okay, you can use such that because we are not mentioning what the program does. So use such that. We just say some programs are structured. So such that X is structured. So instead of R, we use the singular because of X. That means every. I mean, there exists. This is not every because some. Okay, so X here is for there exists. Because we use X as one value. That's why we use is. You cannot say XR structured. Okay, so it's like there exists a program which is structured or such that it is structured. So we use such that because it's not mentioned what the programs do here. We just say some programs are structured. What it does or what the programs do, it's not mentioned here. Okay, so we use such that. So these are the answers. Okay, now if we have something like this, where if is in the middle, I have shown before an example of this in our revision. We're going to start with if. Okay, so you can say if a real number, so you go to the left, is greater than 2, then go to the right, then its square is greater than 4. Okay, because we have x squared here, so its square greater than 4. So R here is real number. So we start with if, then to the left, if a real number is, after if greater than 2, then x squared greater than 4, so its square is greater than 4. You can use any of these sentences as well if you want to. Okay, it's up to you. But the easiest one is the first one. So we have to answer this using that form, using this form. Okay? Using this form, how to answer, how to convert this. So sometimes I will ask you to use this form. This is just a homework. Okay? Use this form to change our sentences, English sentences, into predicate form. Okay? So here we have if a real number. So the answer for this is for all x, because every here are real number, if here. Follow this form. So if a real number, and then this variable x is an integer, so we have z, comma, then it is rational number, it is x. So we use element of, element of, element of. This is element of. It means that this x here is any value of real number. X here is any integer. X here is any rational number. So if a real number, we start from here, go to the left. If a real number is an integer, then it is also a rational number. Okay. For the second one, it's a bit different because we don't have, like two statements merged together. We have only, two sentences merged together. Here we have only one sentence. All bytes have 8 bits. So we cannot have this. But we can still follow the form. For all x, then comma directly, because we have only one sentence. If this one, x is a byte, singular, then it has, so then x has 8. Okay? Has 8 bits. See the difference? Because we don't have 3 elements, 3 domain. Here we have 3 domains, real number, integer, and rational number. Here we talk about bytes only. That's it. That's our domain. So we change bytes to byte. If x is a byte, then x has 8 bits. Here, no fire trucks are green, so all fire trucks are not green. So answer, for all x, if x is a fire truck, then x is not green. Okay, so that's the answer using this form. Guys, this is just for, additional information. Actually, you can use whatever conversions or translations I have given before. Okay, this is just an additional input for you. All right, so all the answer is given here, and these answers are on the move page as well. So that's all for this particular lesson about logic of quantified statements or quantifiers, or we call this also as predicate logic. Thank you so much for watching. Until the next time, bye-bye.